Okay, next up we have one of our tag team presentations. This is coming to us from the Earth System Science Department. We have Dasa Gu, who is a postdoc in Alex Gunther's lab. Dasa got his PhD at Georgia Tech and spent some time with Alex at PNNL. So I guess we also stole Dasa from PNNL too. And then Dianne Sanchez is from Saewon Kim's lab as a graduate student. So welcome. Thank you.
Well, when we as scientists, when we go out into these fields that are very rich in BVOCs, or these plant volatiles that Alex was talking about, we go in there with an arsenal of instrumentation. Our toolbox is extremely robust. So we go in, we build these towers that can be 130 feet tall, that tower above the canopy. We build these rooms that are within the canopy. And in these rooms and on the towers, we house our instruments. And all these instruments complement each other in the data that they provide to us to better understand the BVOCs in these different environments. And ultimately will help us understand the role of these BVOCs in air quality in these environments. So I'm going to show you guys a peek inside our toolbox so you can see what instruments we work with. And so the first instrument I'll talk about is our SIMS OH reactivity instrument. And this instrument is special because it can give us the total amount of reactive gas that we're looking for in a given environment. So it gives us the total OH reactivity of the air. It gives us our budget. However, it doesn't identify the different BVOCs or plant volatiles. So these are unidentified. So in order to identify those and fill in our budget, we turn to another complementary instrument. So we look at the PTR TOF-MS. So this can give us the actual species in real time, and it can identify them for us to help us fill in our budget. So it can give us some BVOCs, such as isoprene. It can give us the total monoterpenes that we're looking for, and other plant volatiles as well. But as you can see, it doesn't complete our budget quite yet. So then we turn to another complementary instrument. So I'll just call this the TDGC for short. But what we can do with this instrument is we can take some samples in the field on these cartridges, and then we bring the cartridges back to the system, and we run it through, and then we can get some more complementary data on these plant species. So we can get isoprene again. We can speciate these monoterpenes so we can know exactly how much for example, alpha-pinene, beta-pinene, or limonene are in that total amount. And we can expand our other plant species. It's a broader range that it gives us. However, you can see that we still don't quite fill in that reactive gas budget. So even with all these instruments, including others that analyze NOx or ozone, there's still a missing puzzle piece. And so these are some unidentified plant volatiles, or BVOCs, and they might be those that are due to stress that Alex was talking about. So what do we do then if we don't know what this piece is? Well, we head out of the forest and we go into the laboratory. And in the laboratory, and so there we move on to the fluxtron, so our big plant chamber that Alex mentioned. And in the fluxtron, we can then make our hypothesis. So perhaps it's something to do with plant stress, perhaps it's drought, or another consequence of this changing world that is causing the plant emissions to change. So we can control our environment, and then we can hook up all the same instruments that we had in the field to our fluxtron, and then hopefully we can get that missing puzzle piece. And now, with this missing puzzle piece from the lab, and from all the data we have from the field, we can use those and implement them into models and improve our models. And then we can really improve our understanding of these BVOCs on a larger scale. And Dasa is going to talk more about these models.
Okay, so in order to find the missing piece discussed by Dianne, we can use model as a tool to make simulations and predictions. For the model, we can use different scale of observations, including the enclosure measurement in our lab, canopy scale of measurement from the flux tower, and also the regional and global scale of observations from satellites, all can be used as the inputs in our model. And here, this map shows the simulated isoprene emission from the mega model which has been developed by Alex and many of our group members. So in this map, we can see over the whole world, most of ice springs are emitted from the tropic forests and some part of Southeast USA and some parts of the East Asia. And there is the biggest hotspot of ice spring emission over the Amazon. So to test our model, we went back to the field again. Then in 2014, we joined the Go Amazon project at the center of the Amazon forest, which has been discussed by Jim and Alison yesterday. So just like this photo, from the air, the central Amazon is covered by similar big trees. So at the same time, using satellite, it tells that the central Amazon is covered by almost one single tree species. Use this information in our model, and we can get simulated ice spring emission with a general homogeneous distribution. So we hope to get more detailed information to improve our model. So we used another tool, aircraft. So by using this aircraft to look closer, we got more heterogeneously distributed ice spring emission. So it means that instead of one identical tree species, there could be hundreds or even thousands of different vegetation species for ice spring emission. And what is more interesting, for the first ever time, we find there are much more ice spring emissions over the high land than over the lower land. There is a linear relation between the ice spring emission and elevation. So now we put this detailed information into our model again. Instead of using the more old, homogeneously distributed emission factor map, now we are using a new heterogeneously distributed emission factor map. So in the model, we got 42% higher ice spring emission. As a result, we get much more formaldehyde from the ice spring oxidation. And at the same time, we got much less air pollutants, including ozone, PEM, and much less OH values. So after that, we think we can put all those detailed information together again and try to find a missing piece.
And so with all these different tools at all these different levels, whether it be in the laboratory or when we're in the field, or the aircraft that's validating our satellites, we can put all this information back into the model, and then the cycle repeats itself, and we get closer to the truth and closer to really understanding plant volatile's role in air quality in this changing world. Thank you.